Hello everyone, I am Pragya Srivastava. I am here to record a lecture on control systems and the course code is KEC 602. In my present lecture, I am discussing stability of linear control systems, and previously we have already started root locus, and in this lecture we are only going to continue the root locus concept. And of course we have studied the rule 1 and 2, where we have studied that how to locate the open loop poles on the S-plane, poles and zeros, and we have to find how many branches will be there. Also, this also have been covered. Now moving ahead, we have to identify and draw that which portion of the real axis will have root locus branches and which portion of the real axis will not have root locus branches. So let's consider this condition where I have this particular S-plane. So what I will do, I will just make sections. Sections will be made according to the boundary of presence of root open loop poles and zeros. So let's this be few sections. So this is section 1, this is section 2, and this is section 3. So I have to see, let's say I am considering section 1. So at this place, when I am considering section 1, I have to see, okay, I am presently studying section 1. Now I have to see the right hand side of the section 1. So right hand side of the section 1, and now I have to count to the right hand side of section 1 how many poles and zeros I am having, the total sum. So it is 2, 1 and 2. So since this count is even, section 1 will not have any root locus on real axis. So in this portion, we will not have any root locus. Let's come on to section 2. Section 2 is this. Now we have to see the right hand side. So in this right hand side, how many poles and zeros we have? We have just 1. So this 1 is an odd number. So because this is the odd number, this section will of course have root locus branch on the real axis. We are not talking about the imaginary S-plane. Now, coming on to the third section. Third section is this. And in this third section, we have to see how many poles and zeros are lying to the right hand side. That is 0. 0 is again an even number. So of course this will also not have. So this is a method to find out the presence of root locus in the real axis. We can also have another representations where we have complex conjugate zeros as well. So let's talk about in this condition. We also need to draw sections here. One section is here, another section is here, then this section is here. So of course, let's say consider this section, let's say consider section 1, section 2, section 3, and then section 4. Section 4, right hand side, we have 1, 2, 3, 4. No, it won't have. Section 2, right hand side, we have 1, 2, 3. So of course, it will have root locus in this. Then section 2, right hand side, we have just this. Of course, we will have this. And then section 4, right hand side, we have zeros. So this will not have. So this is how we can predict the existence of root locus on the real axis. Now, find the centroid and the angle of asymptotes. So centroid is a point where angle of asymptotes will be drawn. Now, what is angle of asymptotes? Angle of asymptotes are nothing but the approximation, the prediction of approximation for the branches which are terminating at infinite or for the branches which are originating from infinite. So it means when any branch will terminate means branches terminating at infinite, it means poles are more. Branches originating at infinite, it means zeros are more. So whenever we have more number of branches and any of the branches terminating at infinite, we have to predict that from infinite what angle will it follow, what angle will it follow and come and reach my S plane, what angle. So that what angle, answer to this question will give will be from angle of asymptotes. So centroid, the formula is very simple: summation of real part of open loop poles minus summation of real part of open loop zeros, and then P minus Z. Of course, we will make a practice after we have done the numericals, and then rule of construction, where we have to find out the angle of asymptotes. Now here we have to find out the angle theta. Angle of asymptote means angle. So angle is defined as 2q plus 1 upon P minus Z into 180. Now what is q? Q will have several values. This theta will have several values depending upon the value of 1. Q, let's say q is 0, let's say q is 1, let's say q is 2. So depending upon different values of q, we will have different values of theta. Theta 1, theta 2, theta 3. So how many q values will you have? We will have q values ranging from 0 to P minus Z minus 1. Let's say we have 4 poles and 3 zeros. So P minus Z is 1 and 1 minus 1 is 0. So Q will have just 0th value, only one particular value, and theta will be having just theta naught. Let's say consider this, we have only 1 0. So P minus Z is 3. 3 minus 1 is 2. So this Q value will be theta 1, theta naught, theta 1 and theta 2. So this is how we have different values of theta. And then again, rule 5 is to find intersection point of root locus branches with the imaginary axis. So how do we do this? First of all, we find the intersection point. Using this method, we can calculate the point at which root locus branches intersect at imaginary axis and the value of k at that particular point by using Routh-Hurwitz method. If all the elements in the row of Routh-Hurwitz are 0, then the root locus branch intersect at the imaginary axis and the vice versa. So imaginary axis means a condition of marginal stability. Marginal stability will come from Routh-Hurwitz only if the complete row turns out to be 0. So the things are related, we can see. We have already studied in the previous method for finding stability. Identify the row in such a way, if we make the first element as 0 and then the elements of the entire row are 0, then we have to find this value of the value of k for this combination. And now we substitute this k in the auxiliary equation and we get the intersection point on the root locus branch with the imaginary axis. Another value where we have to find the breakaway point or break-in point. So this is a point on the real axis where the root locus splits. So from the first slide, we have seen that, let's say this only, the root locus starts here and it terminates here, it breaks here. So this particular point will be called a breakaway point, where the root locus breaks, So to find this breakaway point, what we have to do? We have to find the breakaway point may not necessarily be on the real axis. To find the breakaway point, we use GSHS by DS equals to 0, and which should also satisfy 1 plus k into GSHS equals to 0. And then we will substitute dk by ds is equals to 0. So when we substitute this, we will be having the s value from here. So the value of s, whichever value of s, we have to calculate whether out of these two values, which value of s will be feasible and which will be a relevant and a applicable breakaway point. Next is rules for construction of root locus. Point number 7, where we have to predict the angle of departure and angle of arrival. Angle of departure and angle of arrival will be calculated for those values of branches those branches of root locus which are either terminating or originating at infinity. So actually the thing is, we have to calculate theta d, phi d as 180 minus phi, where phi is summation of angle subtended by all the poles, and phi z is summation phi z is angle subtended by all the zeros. So when we calculate phi, we just do 180 minus phi and then we get angle of departure d. Same thing can be calculated as angle of arrival. Here angle of arrival will be calculated for a complex 0 and the scene remains same. Here we can see that the phi is phi p minus phi z, again phi is phi p minus phi z. Here we had 180 minus phi, here we had 180 plus phi, and of course we will be having the value of angle of arrival and angle of departure. Now let's come and start the real-time example, and the rules which we have studied so far are okay, fine, but we will understand the actual we will understand and learn the actual method to draw a root locus only if we come across a real-time numerical and we solve a problem. So let us consider for a unity feedback system where the transfer function is gs will be equal to k upon s into s plus 4 upon s plus 2, and we have to sketch the rough nature of root locus, showing all the details on it, and then we have to comment on the stability of a system. So let me draw a new diagram where I am drawing the poles. First pole is at s equals to 0, another is at s equals to minus 2, another is at s equals to minus 4. So let's draw 3 sections out of it. This is section 1, this is section 2, this is section 3, and this is section 4. Okay, so here in the section 1, right hand side 3 poles, so of course this will have a root locus. Section 2, right hand side only 2 poles, so we will not have root locus in this. Section 3, right hand side only 1 pole, we will have root locus in this. Section 4, right hand side 0, so we don't have any root locus. So let's start and see, and I want you to predict the nature as well. So of course now from here we can say this section will have root locus. Now I want to start with another color. Let's say I'm taking this red color. Okay, so of course the red cross shows the location of poles, and from the poles it starts. So it has to start from here. It has to start from here. It cannot go this side. So it has to go this side only. Very clear. So let's come into here. So it has to go only this side. So this is why they are showing this black arrow. Till where this will go, we will see it later. Now let's talk about this pole and this pole. Okay, in this section we don't have any root locus. It's written no root locus, NRL. In this section it will have a root locus. So from here we cannot start this way, this side, so we have to start this side only. So we are starting from this pole, we cannot start this side, so we have to start only this side. So we are starting. Do you agree that both of them will meet? Yes, they will meet. And after meeting, they will break, for which we have studied the breakaway or break-in points. Breakaway means they will break and enter into complex plane. That is breakaway. If they enter from complex plane and they go into real axis, that is break-in. So this is break-in and this is break-away. So in this particular case, we will have breakaway. Now, this when it enters the complex plane, will it go straight or will it curve like this? Will it curve like this? That will be defined by angle of asymptotes. Because angle of asymptotes will tell you the approximate angle at which the infinite branches will leave the S-plane. Okay, so from here we have to find out what all we have done according to the slide. We have find out the location of poles, we have done the root locus real axis, and then okay, now angle of asymptote. Angle of asymptote, how many branches are terminating at infinity? 3 branches. So we have to calculate 3 angle of asymptote. Let's go and calculate according to the rules. So rules are, Q will have the value from 0 to P minus Z minus 1. So here P minus Z is 4 minus 0 minus 1. So it is having 0 to 3. Okay. So P, sorry, it's not 4, it's 3. We have only 3 poles. 3 minus 0 minus 1, it is 2. So Q will be having values 0, 1 and 2. So how many angles do you have? You have angle 1 for Q0, angle 2 for Q1, then angle 3 for Q2. You only need the 3 angles to decide about 3 branches. One is this. Which angle will this branch follow? One is for this. Which angle will this branch follow? One for this. Which angle will the bottom branch follow? So you need to have 3 angle of asymptotes. Let's see. They are calculating it. So you are just putting the formula. 2Q plus 1, 180 divided by P minus Z. Q will have 2 values. So first you are putting Q as 0. This is the Q1. Q as 1. This is Q2. Q as 3. So these are the 3 angles. Now, where to draw these 3 angles? The answer to this question is centroid. We have to draw these 3 angles from centroid. Now, centroid, how can you define? We have already learned in literature. Summation of real part of all the poles, summation of real part of all the zeros by P minus Z. Now, real part of all the poles, you have only poles at S equals to 0, S equals to minus 2, S equals to minus 4. So it is coming out to be minus 2. So minus 2 is the point at where you have to make these 3 angles. Minus 2 is the point where I have to make these 3 angles. So these 3 angles will be angles are 60, 180 and 300. So minus 2 पे बनाना है, we have to make it 60, 180 and 300. Isn't it very simple to predict now? This red branch is going the way we wanted it will go. This branch will start from here. Centroid doesn't say that it will start from here, but it will, from here it will go like this. From here it will go like this. See, this is how. Now, how to find out the breakaway point? So, breakaway point we have already find out. We have to find out dk by ds. K you know. K you have to just rearrange this equation and you will find out k. So, dk by ds you are differentiating it. After differentiating it, you are getting the 2 values of s. This and this. Now, you know that the root locus only exists between, let's say this is 0 and this is 2, this is 4. Root locus is only existing, root locus is not existing in this portion. We have written no root locus here. So, no root locus here, it means this value is not a valid value. This one is a valid value. So, it will break at 0.85. 0.85 will be here. It will break here. Root locus will break here. Not here. And then condition for marginal stability. You have the characteristic equation. For this characteristic equation, you see that for if you put k as 48, here you find out here, if you put the value of k as 48 in row where s raised to the power 1 will be having all zeros. So for all zeros, this as will be 6s square plus k, and the maximum value of k will be 48. 6s square plus 48 equals to 0. It means for s square equals to minus 8 or s equals to plus minus j root over 8 will be a s value for which the root locus will go into the other part, that is here. We see this is the value s equals to plus j 0.8. This is the value s equals to 2.8. 2.8. This is the value s equals to minus j 2.8. So this is the overall root locus. We can see that we don't have root locus here. We have root locus here. We have root locus here, here, and then of course this angle is 60. This is 180 and this is 300. That was all about root locus from my side. We will study more on control systems and a few more methods on finding stability in my next lecture. Thank you.